Our first fire aficionado is Dr. Paul Panetta. He has over 20 years of experience in developing measurements of the physical properties of various materials. He's a lab director at Applied Research Associates Incorporated and chief scientist of OMSET. Dr. Panetta does acoustic measurements of various oil properties, including slick thickness, oil droplet size, dispersant effectiveness, herder effectiveness, and in-situ burn rate and efficiency. He's deployed these acoustic sensors on several different remotely operated vehicles and glider platforms in a wide range of sea states. Today, he's going to be talking about direct measurement of in-situ burn rate and efficiency and upcoming Colorado mesoscale and large-scale tests. He has two research colleagues, Rick Byrne and Alexandria Podolsky, who are also making presentations in either sessions 10 or 12, and they'll be ready to chime in to help Paul with some of his slides, and they're also available for Q&A. So Paul, are you ready to go?
Yes, I am, Ellen. Thank you.
All right.
Let me share my screen here and then get into the right mode. And can you see the full screen slide right now?
Yeah, it's looking good. You sound good. You look good.
Thank you very much. I did shave today, even though I'm working from home. And so, yeah, thank you very much for the introduction. Thank you for putting on this workshop, even though everybody's remote. It's been a very good few days, and hopefully everybody sticks in for the next couple days. So I'll be sharing some work that we're doing on in-situ burn measurements. We're doing measurement development and some tech transfer, and I'll share with you what we're doing. So to give you a quick outline, there's really three parts to the talk. There's the measurement science part, the tech transfer part, and then the ongoing field work that we're doing. There's a lot of details here, but you'll see these details again, so I'll go through this one quickly here. So our motivation, everybody knows in-situ burning is one popular response that is sometimes the best response for oil spills. And our motivation here is, every spill is different, every oil is different, so the burn rates and efficiencies are always different depending on the environment and the thickness in the oil. So there's really a need to have a direct measurement of that burn rate and efficiency and to determine how much oil is on the water for the oil budget. So our goal is to develop those measurement methods that are deployable out in the open water. Normally, as many of you know, one would take a nomogram like this here and draw the size of the fire by hand. We think that we can do better as a community, so that's where we're working on it. So this first step is really the measurement science. Most of this has occurred in a previous PESI project, so I'll go through it a little bit quickly, and I'll skip a few slides to save time, but the details are in the slides when you download them, and of course in the reports. So if you see me skip through a slide, don't worry, it'll be there for you when you want to look at it. So obviously, to determine volume, you need the surface area and the thickness. So surface area, there's a lot of drones, a lot of UASs that people have seen out in all of these talks. And so using drones and imagery from the cameras is a great way to get the surface area. And this here is just a image of some mesoscale burns that we did back in March of 2020. And here's oil on the water here. And then Rick Byrne has developed algorithms to rectify that image and identify the oil and then do a pixel counting with knowing some known dimensions to get an area of the oil in this particular scenario. He's worked with many different camera systems, both visible and IR, and he's developing the algorithm so they're independent of the UAV. I'm sorry, independent of the UAS, independent of the camera, and there's several steps that need to go through there. For the thickness, we're using acoustic measurements. If you've seen some of our work in the past, you will know that we do a lot of acoustic measurements of thickness and oil properties. In a simple sense, it's very much like sonar. there's a ping. The sound goes off and hits the bottom of the slick, hits the top of the slick, and they both come back to the receiver. In this particular image on the left, each vertical slice is an individual ping from the sensor. The vertical dimension here is the thickness, and the horizontal is just the amount of time that you're running your sensor for. So as I mentioned, the sound bounces off the bottom of the slick because of a difference in the density and the speed of sound in the two different liquids. When you look at the image, you'll see a reflection here from the bottom. This region is the slick, and then a reflection from the top. By knowing the speed of sound in the liquid, we can calculate the thickness simply by measuring the distance and the amount of time it takes to get between the two surfaces of the slick. It's a very simple measurement. It's one of the things that we can do with the most accuracy. These kind of measurements are routinely used in many other communities, medical ultrasound, aerospace, and we're just using those capabilities here for high resolution, high accuracy measurements. As Alan mentioned, we've deployed these on many different platforms, 4 different ROVs and a glider. We've done it handheld, frame mounted, in labs, tanks, lots of different things over the years. And here's a few different pictures of some deployments we've made over the years, starting back in 2013, 14. For an ROV, we developed an OMSET to roll along the bottom of the tank, and then several different commercial ROVs and gliders. So what you're going to see is some results from some burns we did here in Colorado in the last few months. And there's a lot going on here, but I'll walk you through it. This is at a fire safety training center nearby. And we've set up in this space, we have our burn pan here. And for this particular project, the Department of Interior has restrictions on drone use throughout the agency. So because we're funded by BESI, we're not allowed to use drones on this project. So to simulate drones, we put cameras up on cable systems here. This is what's called a wire-all, and it's really just a cable camera system that moves along a cable, very much like you would see at the football games, except this one is much smaller and much less expensive and mostly plastic, but still pretty rugged. So these move the cameras back and forth to simulate what a drone might do to give us the opportunity to use, develop the algorithms for rectifying and the instantaneous measurements. So overall, in all these sets of experiments, we've done over 100 burns, lots of different oils, several different locations, several different length scales, and you'll see some of those results in some pictures and videos. So a little bit more on the measurement science, so I'll focus in on what we did so we can show you how we can get the results we can. So here's our 1 meter diameter burn pan. We put multiple acoustic sensors in the bottom, 8 of them to measure the thickness, and then a thermocouple tree in the middle here to measure the temperature inside the burning slick. We typically start with an initial slick of about 10 millimeters, and we have the thermocouples arranged 1 millimeter apart vertically so we can get the gradient of the temperature inside the slick as it's burning, as well as in the flames and in the water. Then we place all of this on top of a high resolution scale so we can get the burn rate and efficiency directly just from the mass loss, and then use that to benchmark our acoustic measurements. And then of course, surface area from image processing. In this case, surface area is not so interesting because it goes to 100% coverage, but these particular burns help us with some of the logistics and processing. So I'm going to show you a video of what we did. And if this is not coming through, please let me know. What we did, this was in January. We also did burns in December and October. We did a live WebEx of these burns, and we did it so that several reasons. Some of it is people can stay connected and see what we're doing. And then the other is so that people, sorry about that, the audio was on, so that people can see what we're doing, stay connected, and understand what the burning is like, because a lot of people had not seen live burning. And as Robin Conley mentioned earlier in the week, it was a nice way for people to at least vicariously live through us and do some lab work. So what you're seeing here is visible camera and an IR camera that are fixed to a tower. And then these two that are jerking around are the two camera views from the cable camera system moving back and forth. And again, we were not looking for perfectly stable. We were looking for something one might expect from a drone moving around quickly. So these may not be visually appealing right now, but this is exactly what we wanted to see. And what you're seeing building up over here on the right is the acoustic signal of the during the burn, as well as the temperature on the right-hand side. So again, we did this, you know, there were a lot of COVID restrictions. Rick Byrne couldn't come out. Our Bessie program manager, Karen Stone, couldn't come out. So we wanted to bring them in as at minimum. And then of course we sent it out to several other people. And some of you online may have seen some of these burns as well. And so I will skip forward a little bit so you can see how this builds up. And I got a lot of good feedback from people that, hey, this was great. Some thought it was entertaining. Some said, oh, I just got a bag of chips and sat back and watched. Others, it was able for us to collaborate, and they were able to see us get residue and say, oh, geez, can you come over here and look at this view or this view? It was very good overall in this time of COVID in terms of how to interact and how to do work together. I'll go a little bit forward. Not sure if you can see this on the right, but you'll see a closer up view of it in the next few slides. Again, this is bottom of the slick, top of the slick, and the temperature. And you know, we're going through discussions with people online to share what's going on. This happened to be alpine with a 15% emulsion. So I'll move on from there. So what you saw a little bit in the slide was the acoustic signal. This is the bottom of the slick and the top of the slick. We ignite it at this particular moment and then measure it as it burns throughout the burn. At this particular point, the water underneath reached 100 C and started boiling. So you can see the water shooting through the slick and into the atmosphere. So this is fresh oil here. There's not much going on here until there's boil over. And then from measuring the time distance between this region here and knowing what the temperature is, we can get a thickness as a function of time. So in this particular example, we started with about 11 millimeters of oil and it burned down over time. The green is from the scale and the purple is from the acoustic measurements. We don't get perfect agreement because it's very difficult to account for the temperature changes, but you'll see in the next slide or so that we get pretty good agreement from our measurements. So again, the thickness drops over time, and then after the flames go out, it stabilizes. During this period here, it boils over, and the burn rate and efficiency we get from the slope, and then the efficiency from the start to the end. In normal circumstances, if you're just measuring the mass before and after, one would assume it's a straight line. Clearly, that's not the case, and that's important. You'll see in a few slides. Checking the time. So I'll skip through this a little bit quickly, but from our measurements of thickness from acoustics and thickness from the scale, the straight line is a perfect fit. And you can see our points are very, very close to the actual measurement from the mass loss. And our accuracy is within 1% during that time. Boil over is not quite as good. But again, we don't expect to see that in the open water anyway, so that's not so critical, but we get a very excellent accuracy and precision of our measurements. So I'm gonna skip past that one. Ellen mentioned that a few other of my colleagues will be giving talks. There's the list of where they're gonna be. Here's the oils that we used. The purple boxes are the oils that we have burned, as well as Hoops and Thunder Horse. And right now I'm just showing you the viscosity at 20 C. There's much more data in the extra slides that you'll see if you download them. And then if you want to see herder effectiveness on all 14 sides, it's all 14 oils and dispersion effectiveness on 10 of the oils, check out these 2 talks by Rick and Alexandria. But overall, we've done over 100 burns and collected a lot of good data. So I'm gonna skip past this one because this is in our report and you can see this in the slides. The only take home right now that you can see is that we can measure the thickness as a function of time, many different types of oils, large range in viscosity, and get an instantaneous burn rate and efficiency for these types of oils. So I'm going to jump forward. I'm checking the time to look at the tech transfer and share with you what we're doing there. So a lot of times people would do a stop right there and say, okay, we're done with our experiments. But what we're really doing is using all of those accurate and precise measurements of the burn rate and efficiency to develop our measurements, to deploy them out on ROVs and drones. So we're really flipping the switch here and going to deployable systems. And there's really 3 different aspects. One is weathered oil, because you're never going to get to the oil immediately. It's either going to emulsify, evaporate, photooxidize, or other things. And then there's going to be larger scales, the oil is going to be moving. And then so you have to think about your sensor deployment. So us, it's ROVs and drones. For the ROV, we're in the process of integrating our acoustic system onto the ROV so that it's all contained and all battery powered within that unit. For the weathering, we only evaporated and emulsified because for testing and developing the methods for thickness measurement, it's the emulsified oil that provides the biggest challenge, and you'll see what that looks like. So we went through several different levels of emulsification, and this is just a quick snapshot of what the oil looks like when it's fresh, and then after you mix it, here is 35 hours with salt water, and you can see they're very, very small water droplets, and here's a blow up where you see lots of small droplets around the droplets. So these are the oils that we burned recently: Hoops, Alpine, and Rock, fresh, and 5, 10, 15, and 20% emulsion. That was done just in the last few months. I'll show you data on the Rock. Again, this is what the acoustic signal looks like. We have the bottom of the slick here and the top of the slick. The emulsion is quite different. It's a little messy over here. You can ignore that if you like. Again, the bottom of the slick is here, top of the slick is here. And because it's an emulsion, you see a lot of scattering from the water droplets inside the slick. And again, this is only about 1 centimeter thick. So one of the questions that everybody asks when the oil hits the water and the boats get out is an emulsion present? So as a measurement science people, we say, yes, we can measure that. A lot about the next question about the emulsion is what's the water content? We're working on that. We're in the middle of this part of this project, so we haven't quite solved that yet. And the same with the water size, the water droplet distribution. Those are all important for the fate and transport. What's the burn rate and efficiency is also critical when you burn an emulsion. And yes, of course, we can do that. And I'll show you some results. So again, this is a little busy, but I wanted to show you all the data in a snapshot. So this is the mass loss as a function of burn time, starting at say 100% of the oil and then down past 0 because some of the water boiled off. This blue line here, this first one is fresh, and then 5% emulsified rock. Black is 10%, purple is 15%, and then green is 20%. And you can, what we do is we calculate the burn rate from the slope. What happens right here in this area is we're boiling off the water underneath the oil. So we don't account for, we don't use that information when we calculate our burn rate. We use this data in this space. This bump here is because we had to add diesel to accelerate the fire. And we get a burn rate and an efficiency based on this mass loss. And we're doing the next step to work on the acoustic measurements to determine those as well. Burn rate was very high for the fresh, and then it dropped for the emulsified oils. It's not a surprise. There's a lot of water in there, and didn't burn as quickly, burned for longer period of time. The efficiency was still 90% for the fresh, and then it dropped some for the emulsified oil, but still stayed pretty high for this rock emulsion. Then I'll jump to the field work, go through these quickly. We had a good site in 2020, since 2020 was kind of a dumpster fire year. We affectionately refer to this as our dumpster fire burns. And we used a DJI drone. And in this case, we were allowed to use a drone because this was through an MPRI project back in March, and then acoustic measurements from an ROV, and had two different scenarios, one with a simulated boom, and then free floating oil, both with and without herders. And I'll show you a quick video here. This is a video of the burn. So poured the oil is spreading out. What we're doing here is calculating the thickness in the area. The blue is the thickness. You can see as the oil is spreading, the thickness is going down, surface area is going up. And this image here on the top left is directly from the drone. If you look at these two on the bottom, they jerk around a little bit, but that's because they're rectified and keeping and centered so that Rick can identify the oil and calculate the surface area. So we turn on an ice eater, which is just an underwater motor with a propeller on it, to push the oil back. And I'll get to that point again. So the thickness is going down as it's spreading. And then ice eater turns on, the small wave hits the oil, starts pushing it back. Thickness stabilizes, and then thickness starts going up, surface area starts going down as the oil starts contracting. So I'll jump forward, almost done here. I'm looking at the time. So we're planning some mesoscale measurements here in Colorado. We're putting together roughly a 40 by 40 foot tank. We'll put oil there, do multiple burns. And then later in this year, we plan to go out to Poker Flat. And this is just a stick figure version of where those cameras would go and where the burn will be. So we want to now transition all of that highly accurate set of measurements to the ROV and drone in these two particular environments. Now we're advancing the technology quite quickly. In the first phase of work, we went from TRL2 to TRL5, where we did measurements in a relevant environment. That was through 2018. And then in this next phase, we're looking at emulsions, and then ROV deployments, mesoscale burns, large scale burns. And then we're planning to be involved with the Canadian measurements for their field releases in 2021. So that will give us a real field release for these particular measurements. And then we have a conceptual diagram here of how we might deploy it on a real spill in the future once it's commercialized. So to conclude, we've developed accurate burn rates and efficiency, and that information is critical for the accurate volumes of the oil that's in the water and how much burns. The measurements of the burn rate and efficiency, to do that, we've determined what the surface area is, and then a direct measurement of the thickness. And we can get instantaneous burn rates about every 2 seconds with the way we're set up right now. So we're working on transitioning that out to ROV and drone platforms. For technical results, obviously the burn rate and efficiency decrease with increasing levels of emulsion. And in future talks and publications, you'll see the other data on the other oils. And then, just in a lab sort of setting, this technology could be used for burn rate and efficiency right now, and the volume of oil, so that people can study their particular methods of burning and determine how well they're doing. And then, as I mentioned, we're integrating this into ROV and drone platforms for real-time measurements on real spills. So I just want to thank you for your time and take any questions. There are many people who are involved in the project that are listed here. We have 2 publications from the first phase of work, one at IOSC, and then of course our Bessie report that was peer reviewed by several experts in the field. And I'm happy to take any questions. Thanks.
Thank you, Paul. I've heard all or bits of your presentations about 3 times now, and I never fail to be fascinated. And you're doing really interesting stuff. Lindsay, how are we doing on questions for Paul?
We have one question from Adam Kaiser. Is there an ability to use the acoustic measurement of oil thickness from a UAV as opposed to the ROV?
There's a couple different ways to do that. For us, we have the sensor in the water and use the water as a couplant. You can go from the air, but then propagating the sound through the air into the oil and then back requires a different technology. If you look back in the, I think it was 80s, the Canadian NRC have some very smart people who put together a laser-based acoustic system that did just that, where they shot a laser, generated an acoustic signal in the water. It bounced on the slick, through the slick from the top, and then they received that signal with the laser again. That's a good way to do it. It's obviously expensive, and because of the laser setup, and there's a lot of sophisticated things that are needed for the laser. We chose the ROV and the sonar route because it's ubiquitous. It's everywhere. ROVs are everywhere, and they're getting cheaper and cheaper. And putting sonar in the water has been going on for so long. So that's why we chose that route. Thank you.
Thanks, Paul. We have one more question. It's a 2-part question from Stephen Tuttle. How do you account for the change in oil properties as the slick burns? And how do changes in oil properties influence the acoustic behavior of the oil?
I'll go to the last one first. The acoustic properties for different oils, what we're doing, and I didn't put in this talk, but it's in the report, is we measure the speed of sound as a function of temperature for the oils in the lab first. So we know how that changes as a function of temperature. And we also measure the soil. We also get those acoustic properties at room temperature. Now, when it's burning, we go through that calculation of using the speed of sound as a function of temperature to get the thickness. We have found for all the oils that we've used, they're really not that much different from each other. They have a very similar behavior, but we're still measuring all the speeds of sound as a function of temperature. So that's how we account for the changes in the properties as it's burning. It's not perfect. There are some assumptions we have to make, but you see that our agreement still is really quite good.
Okay, thank you. We don't have any further time for questions. In fact, we may be at this point running a little bit behind, but I think that's kind of the nature of these presentations. I mean, everybody, I don't think it's just me. I think people are fascinated by the research and the conversations that result from the research. So thanks, Paul, for getting us started on this session today.